All right. Welcome everybody to the Midwest Azure Microsoft 365 user group. Today is February 24th, 2021. Hope everybody's having a good day. And just to kind of go over group mission, inclusive environment. We want to have a nice learning environment and welcome anybody that wants to provide sessions and invite their colleagues to attend. You're welcome to do so. For some upcoming presentations, after today we're having Shabazz Dar back in about a month for Endpoint Manager and Autopilot. He did a good WVD session a couple months back. We've got Data in Azure with Matt Bradley. We'll have our speaker today back for another session here in about 8 weeks to just expand upon the topic he's doing today, and then we have a couple new speakers that haven't been with our group before, with John Colberth to talk about YAML, and Chris Reddington to talk about GitHub deployment for podcasts and blog sites. So our speaker today is Lenni Lobel. He is a data platform MVP out of New York. I'll let him do a formal introduction here in a second. And what he's going to be talking about today is giving everybody an introduction around Cosmos DB. So without any further ado, I will turn it over to you, Lenni. I'll stop sharing and let you take over the screen.
Thanks, Wayne. If I could just get that screen share.
Yep, welcome. You should be able to grab it now. Yep.
Glad to be here nonetheless, and this is an introduction to Cosmos DB. If you're not familiar with Cosmos DB, this will give you a real good introduction, and even if you are, we'll hopefully have still enough depth in this overview for you to learn something new. My name is Lenni Lobel, and I run my own company here in New York called Sleek Technologies. I'm also a principal consultant with Talon, a data platform MVP. Those books on the right are really old by now, but more recently I have Pluralsight courses on SQL Server 2016 features, as well as a bunch of Cosmos DB courses on Pluralsight. So by all means, check out those resources, reach out and contact me. And my contact info is there at the bottom of this slide. I've got this link here where if you visit this link, you will hit my OneDrive, and then you'll be able to download a zip file, and inside that zip file we'll have this entire deck, as well as the sample code to go with it. All right, so what our agenda is, and it's a little ambitious to get it all done in an hour, is to have this really broad overview and cover a lot of things in the overview, with a focus on, or digging a little bit deeper later on, into throughput and cost and horizontal partitioning. And these are really core critical concepts, as well as global distribution. At the end, we might just have a little bit of time to scratch beneath that surface. And with that, I'm going to just jump right in with our overview. With Cosmos DB is a NoSQL platform. If you're not familiar with NoSQL, it's all about big data. Most of you are. Most people by today are familiar with big data and the 3 Vs, volume, velocity, and variety, which corresponds to storage, throughput, and schema, right? Where scale-up architectures like SQL Server only scale up to the size of about one box. At some point, you can't scale up anymore, and really the only way to scale is to scale out by adding multiple servers. All right, and so therefore, a NoSQL database is built to be distributed from the ground up. There are going to be replicas available to make sure that the data is always available, even in the event of a failure, and as well as just having additional replicas for performance reasons. It's built to scale out automatically. So if your storage and or throughput needs exceeds that which one box could handle, there's a scale-out architecture behind the scenes where there's a cluster of servers that back your database, and therefore you get elastic storage and throughput. And it's schema-free, right? The variety aspect. There is no enforced schema. There is no defined shape. If you're coming from a relational background like SQL Server, this takes quite a bit of getting used to. It doesn't just mean that you don't define a schema. It also means that you model things very differently, the topic of which will be my next session on Cosmos DB in April. But for now, just understand that you don't define a schema, you don't define the shape of your data in any NoSQL database. So this is like, these are general NoSQL concepts that are not specific to Cosmos DB per se. Cosmos DB is a massively scalable NoSQL database hosted by Microsoft in the cloud on Azure with service level agreements to the 5.9 percentile, as they like to call it, 5 nines of availability, which if you look at 4 nines of availability, you are going to be guaranteed no more than 52 minutes of downtime over an entire year. And if you bring that up to an additional 5th nine, a percentile, then you're guaranteed you'll never have more than 5.2 minutes of downtime a given year. And you can achieve 5 nines if you globally distribute your data. It is extremely fast. Your point reads and writes for on a document level to read and write a document it will usually be 10 milliseconds or less. It will automatically partition your data out and your throughput out across a cluster of servers completely automatically, unlike the early days where you had to manage that yourself. So you get elastic scale for both storage and throughput. It is also built from the ground up to be globally distributed. You just point and click on a map and your data gets distributed. And you can also have multiple write regions. That's the multi-master feature, where users, wherever they are in the world, will be able to enjoy that single-digit millisecond access time for reads and writes wherever they are in the world. And in accordance with the kind of schema-free nature of NoSQL, Cosmos Cv also has multiple APIs and supports multiple data models, where each API roughly corresponds, the API roughly corresponds to the model. And so, but it's not exclusively necessarily, as you'll see, limited to JSON documents. It also supports tabular structures, graph data models, which are composed of nodes and edges or vertices and edges, as well as columnar, where you ironically would define a schema. So how would you get started with Cosmos DB? There's a 30-day free trial that has been around for a while now. It requires a Microsoft account, of course, but it does not even require an Azure subscription. You just go to that link and you try Cosmos DB for free without even having a Cosmos DB, an Azure subscription. Of course, the conventional way is to go to the Azure Portal, and you need an Azure subscription, of course, and there is a free tier, thankfully, which is really nice. This is relatively recently added. It might even still be. No, it's not in preview anymore. The free tier is out, and basically you get your, if you have modest storage requirements and modest throughput requirements, it easily fits within $24 a month, and you will be covered for free. While the 30-day free trial, after 30 days, your data gets destroyed, and you can always sign up for another 30-day free trial. There's no limit to how many times you can do that, but each time it knocks out your data. With the free tier, it's regular Cosmos DB. You just choose apply when you're setting up your account. There's also a local emulator, which I don't use. I mean, I used to use it, before the days of the free trial and the free tier, but if you want to, you can download the local emulator and have it work on your local machine. And in most respects, at least all respects, as far as development purposes are concerned, it emulates the real service, and you don't need an internet connection. So let's go walk through a demo of what it's like to create a Cosmos DB account. So you head off onto the portal and you click on the hamburger over there and choose create a resource. And then you choose Cosmos DB, right? And like almost any Azure resource you create, you choose a subscription and a resource group. And if I'll go ahead and choose my Cosmos Demos RG resource group to contain this account. And then you define a name for the account, which has to be globally unique. And if I choose a Lenni demo, you can see over here on the right, oops, sorry. You can check mark letting you know that that name is available and you can use it. So I'll name my account Lenni demo. I'll just scroll down a bit And the next thing you choose is the API. And you can see that it is already selected to be the SQL API, also known as the core API, not to be confused or having anything to do at all with .NET Core. It just means that, this is really, the truth is this is the native API. If you've been following the history of Cosmo Cv from the early days, when it was actually called DocumentDB, and it was limited to, no, I shouldn't say limited. It was limited to JSON documents, and it used this API, and it uses this integration point, if you will, this API. But you click the dropdown, you'll see that besides for the SQL API, there are other choices. Because again, now Cosmos DB is multi-model and supports a variety of data models and therefore APIs to go with them. And I'll talk a little bit more about them in an upcoming slide. For now, we're going to stick with the core API or the SQL API, which means that you're working A, with JSON documents, and B, using some form of SQL dialect to query those JSON documents. Location. And you can see I didn't highlight it, but there is a new, this is what's still in preview, serverless, which we'll talk about. And that's just a capacity mode that you'll learn more about in a bit. There's the free tier. Let's say you can have one free tier within a subscription. And I'm going to go ahead and choose and create to use my free tier now. This next one, account type, is really unimportant. I don't even like the setting here. It doesn't actually affect the service in any way. It's just it just influences UI defaults to be either more appropriate for production environments or more appropriate for non-production environments. But it's just UI defaults that are affected by this setting. It doesn't really affect the service in any way. And I'm going to leave it in non-production. And then you've got the geo-replication controls here for geo-redundancy, which is global distribution, and multi-region rights, which is multi-master, the ability to write to multiple regions as well as read from multiple regions. And you can see here that if I choose enable, Cosmos DB will automatically, since I've chosen West US, it'll every Azure region has a buddy, and by default, that's for West US, that's East US. So by default, if I choose enable, West US will get paired with East US. But I'm not going to click it now because I can really pair West US with any region and multiple regions throughout the world at any time. And then also at the same time, I can enable multi-master, multi-region rights. So for now, I'll just leave these settings the way they are, hit review and create. Can I just do a shout out to make sure that everyone can still see my screen and hear me?
Yeah, we're good.
Oh, okay, great. So I'll just review my settings, and you see it can take a bit of time, more or less, depending on what region you choose and perhaps some other options that you've selected for the account. And then you go ahead and click create. And that will take a while, and the deployment will run, and then it will be complete, and you will have your Cosmos DB account. You will be able to click on go to resource, and you will be right there on the quick start page, which is, I find, a rather useless page. It pops you there by default, but you really want to click on the overview tab and have a look at the overview, where you can see that the read location and the write location, and notice they're pluralized because there could be multiple read and write locations, but right now we only have West US for both. And there on the bottom left there, if I click on keys, I'll have access to the account keys. The URI, which is, first of all, essentially the account name that you've chosen. I chose Lenni Demo, and it was available. So the URI is composed of that account name with .documents.azure.com on port 443. And in order to access any databases or actually anything on that account, I'll need access to a master key. And there are two of them. There's a primary and a secondary. And the reason there's two of them is for rotation purposes, which I won't get into, but you just really need the primary. And the connection string is really nothing more than a combination of those two things that you need. So to connect, you need the URI, which is the account name, and a master key. You need those two things, either supplied individually or Depending on the API or the SDK that you're working with, you might combine those two things as the account endpoint and the master key inside of one connection string, right? Where the secondary connection string uses or embeds the secondary key, and the primary connection string embeds the primary key. Okay. And at that point, you're going to want to start getting busy with your account. So you'll go ahead and click on Data Explorer. And right now things are empty because we have a brand new account with no databases and no containers. So the very next thing that we'll want to do is create a container. I'll go ahead and click New Container, and the blade opens up. And containers belong to databases. So almost and very loosely speaking, one database has multiple tables in SQL Server. In Cosmo Cv, one database has multiple containers. So you really can't create a container without creating a database or creating a container for an existing database. And you can make that choice here. I'm going to go with a very simple example. I'm going to create a database called Families. And you'll notice that I'm being asked if I want to provision database throughput. This is actually not a good default. This should be unchecked by default. And you know, I know why it's checked by default, but I can't get into that discussion. But it should really be unchecked. So you should not be setting throughput here. This is a number here. You see 400. We'll talk about what that means. But a higher number will give you higher throughput and more hardware provisioned for higher throughput at the database level. But that means all containers within the database. And you don't really want to do that. You really want to provision throughput at the container level. So one container needs more throughput, one container needs less throughput. If you provision throughput at the database level, it gets evenly distributed across the containers, which you generally do not want. So I will uncheck that. And you see that option now to set the 400 goes away. It's actually been moved down here. Here's the 400 now at the container level. So I'm not provisioning throughput at the database level. I'll do it at the container level. But first I have to create the container, and I'm going to give this container a name, and I'm also going to call it Families. This is a ridiculously simple example. I only have one type of document, and they're families, and that's all I have. In the real world, you would have many different document types inside of a single container. So when would you have more than one container in a database if they can share multiple types of documents? And the answer to that has to do with partitioning needs and throughput needs, but not differing types. It's not like in the relational world where you have 5 different entity types, you would create 5 tables for them. No, you could actually and would actually combine all those 5 types in one container if they all share the same throughput needs and they share the same partitioning needs. Those are the defining characteristics of a container. It's provisioned throughput, how hard can you hit it, and its partition key, like how is data physically grouped and organized within that container, regardless of the type. That partition key. This is the all-important partition key. And this is how data in the container is going to be partitioned. And we'll talk more about that. But for now, just understand, I'm just going with actually, if you look at the suggested default, I'm going to go with it. And because of the slash notation there, is an indication that we have a zip code property that's nested beneath an address property in every document in this container, and that value in that zip code property is going to be essentially the grouping of all the physical groupings behind the scenes. All documents that share the same zip code, for example, will be in the same, what I'll call logical partition. And then scroll down a bit and set that throughput, and that's the same value that we saw above. So again, you see, you can go up to 1 million. The fact is that you can go above 1 million. There's no practical upper limit, but they want you to contact them if you need more than 1 million to kind of discuss it, like see why you actually do need more than 1 million. 400 is as low as you can go, and you're going to get, and it's going to cost about $24 a month, as you can see. So also you'll notice this auto scale option, which is relatively new. It's so there are 3 different ways you can provision throughput: manual, which is actually, I would say, the recommended way. Auto scale, you get automation, but it actually costs more in most cases, but it gives you a lot of conveniences that you don't have to worry about, but you pay for it. And then there's serverless. which you don't provide any throughput, and it's just consumption based as well. But we'll just leave it with 400 request units per second, or RUs per second, and we're going to dig into what RUs mean a bit more. And now you can see I've got my families database, which if I expand it, I've got my families container, and if I expand that, I've got items and some other things I can click on there, including what looks very familiar as store procedures, user defined, and functions and triggers. Since I won't be talking about those at all for the rest of the session, I'll just mention here and now that these three things, store procedures, user defined functions, and triggers, they don't necessarily work the way you think they do, but they are server-side code. They run in Cosmos DB, but they're written in JavaScript. Okay, and they're transactional, which is store procedures, that is, are transactional in the sense that you can have a store procedure update multiple documents that share the same partition key. They're scoped to accessing documents within a given partition key, which is another reason why the partition key can be important, because that store procedure can then update multiple documents. And if the store procedure fails with an exception, or if anything, any of the updates fails for any reason, everything rolls back, which is a very compelling aspect of Cosmos DB. You don't usually get transactional capabilities like that in a NoSQL database. So then at this point, now that we've got a container, inside of a database, we're going to want to create documents and store them in that container. But you'll usually do not this way, either programmatically, like your application is going to do inserts and updates and deletes, or you'll have migrations like Azure Data Factory doing large-scale migrations of pulling, ingesting data into Cosmos DB. But you can also just click on the items link and hand type a JSON document if you like, which is what we'll do here. And I'll click New Item. And here I'm being given like a placeholder a document starting out with an ID property. So your JSON documents are schema free. You are free to define any shape you want, any schema that you want. There's only one required property, and that's the ID property. And the ID property is not to be don't be misled into thinking that it is a unique value within the container, within the entire family's container. No, it is a unique value within the logical partition defined by the partition key. So in our case, within a zip code. So you could have two family documents, okay, with two different zip codes having the same ID, right? And if you don't supply an ID, and very often you won't need to or want to, then, like I'm doing here, I've just replaced that document and I've hand typed to this JSON document, and I'm not providing the ID property. What will happen is, I shouldn't say Cosmos DB will automatically generate a GUID, because accurately speaking, Cosmos DB will throw an error. But the client application, in this case, the Data Explorer, the UI, the front end, will see that you didn't supply an ID, and it will generate a GUID and provide that. But if you look at this document here that I've typed, first of all, I haven't defined the schema here. That's one thing. I didn't have to define what these properties are or what their data types are up front. Let me actually click Save first. When I click Save, it gets saved to the database, and we get these kind of additional properties down here, including the ID. Like I said, the Data Explorer saw that I didn't provide one, and so it provided one. And then that was on the front end. Okay, because you have to provide an ID. If you're writing your own code, you will have to generate a GUID if that's your intent. But Cosmos DB, upon insert, will attach these additional system properties, which I'm not going to talk much about. Notably, this is the timestamp. This is a really important one, really. It's the timestamp. This is essentially like an epoch value, the number of seconds elapsed since, I think it's January 1st, 1970. The point is that you can look at that value and know when the document was most recently inserted or updated. Here I can see the ID and the partition key, the two things combined, which makes the document unique. What's a little funky is that because the ID is a GUID, then it's unique across all zip codes, which is which can be handy if you need to change your mind about the partition key, which is a big headache. But if you do need to do that, you need to migrate data from one container to another, the same data, but partitioned on a different value. It's knowing that you have an ID, the GUID as an ID will mean you'll never have a collision when two documents that used to be in different logical partitions now wind up in the same logical partition. Having the ID as a GUID means you'll never have a collision, because this is obviously unique across the entire container. Another interesting thing to note is the way I've modeled this data. So here I've got a nested array of strings. Now, I've just used strings to make it short, but imagine this was a nested array of objects. So in the relational world, there would be multiple tables where you have there would be the parent row, and then in the array, all the objects in the array is what you would normally put in some child table related on a foreign key. And the same thing here. And again, I'm just using strings to keep it short. Here, there's a nested object, not a nested array, and that, again, in the relational world would be like a one-to-one, like the address would be in some other row with a one-to-one relationship, not a one-to-many. But you see, I've embedded all that here, and that's all part of a data modeling discussion that we'll have much more in depth in, on my next Cosmos session. Yeah, there are all the properties, the ID property, the data explorer added, as a GUID, and then the system-generated properties that are prefaced with an underscore. Here, I'll go ahead now and add another document, and one of the nice benefits of Cosmos DB or any NoSQL platform is that because you don't have to define the schema, new properties, it's not disruptive to introduce new properties when you need them. Suddenly, I have a new family that has a pets property, which I never needed before, but no problem. I'll just introduce a pets property as a new array. And you'll also notice that the zip code in this case is a different value, and that means that these two documents are in different partitions, different logical partitions. Right, that's the new property that I've introduced in the second document. And there are both documents. And well, let's kind of wrap up this sequence of demos with the very natural thing you'd want to do at this point, which would be query, right? So you started from scratch by creating an account, then creating a container with a database and provisioning throughput and defining a partition key. And then you loaded some data into that container, and now naturally you want to query it. And we're going to do that in the Data Explorer by clicking New SQL Query and bang out this, what looks like a very simple select statement. And it looks very approachable and friendly if you're used to T-SQL or a relational database dialect of SQL. But it's actually quite different and works quite differently. The asterisk, first of all, unlike in the relational world, is not a bad thing. In the relational world, you really shouldn't be using select star in your production code, in your application. You should always list out the columns that you want. But in Cosmos DB, it's really the only way you're going to get a document out of the container exactly the way it's shaped in the container. Because from one document to the next in the container, it can be shaped completely differently. And if you supply anything other than the asterisk, you are defining a shape that every document returned from this query is going to look like. So that's why select star is actually needed or handy. In many cases, not all cases. You can, of course, list out just the properties that you want as well. And the other thing to point out is the dotted notation here, which means that you are doing some navigating via this path. It's very common to refer to the container as C. So notice the container name, families, is not anywhere in the select statement. The select statement runs in the context of a container, whatever container it's running in. So the very same statement in another container is going to not necessarily have to be changed. C is very often used as an alias to mean container, and that's the root of the document. Each document in the container, there's an address property and a city property nested beneath it, and I want to get all those in Chicago, and I'll execute the query, and I'll get two documents. This is what's called a cross-partition query, because one is in one zip code and one is in another. And that means that behind the scenes, Cosmos DB had to fan the query out across the container to find all the documents whose city is Chicago. And that's obviously less efficient than a single partition query. It doesn't mean that it's evil. In fact, it's certainly not evil. It's only evil if that's your most common querying pattern that you're doing over and over, especially in high volume and with high velocity, then it can become evil. This one is a single partition query because I've included the zip code. I only have one document because I only have one family in the zip code. But if I had many families in this zip code, they would all get returned. And I could further filter on the zip code to get those, I don't know, within the zip code where household salary is greater than 80 grand. I don't know, just making something up. Imagine that was in each document. That would be further filtering on the families in that zip code. So it would still be a single partition query. I just get the one document in this case. What about that pets property, right? It can become a little problematic if some documents have the pets property and some don't, and you need to get the ones that do, and you don't even know if the pets property is defined, and this is telling you if it's defined, not if it's there and its value is null. It's not the same, right? It could be there and its value is null, and that means it is still defined, but this is going to give me that one document that doesn't have that pets property at all, or that does rather have that pets property and not the one that it does where it's not defined. Yeah, array length, just showing you different examples here where, the kid, again, this is schema free. So there's an assumption here, not every document that comes out of the container is going to have a property called kids. And even if a document does have a property called kids, there's no guarantee that the kids property is an array because this is schema free JSON. The kids property could be a number or a string. But if there is a kids property and if the kids property is an array, then this function is going to return the number of elements in that array. And give me all the family documents where there is a kids property that is an array that has more than 2 elements, essentially. And those are my 3 kids, Adam, Jacqueline, and Josh. All right. Whew. So let's see where we're at. Management options, different ways that you can manage Cosmos DB. By the way, I should mention that feel free to shout out questions or if you need to, but I'll pause now at this point to see if there's any questions to this point. All right, silence is compliance. Am I still live out there?
You are still live. Yep, I just
right.
checked the chat. There's nothing in the chat, and I guess nobody has any questions right now.
Fantastic. Well, that's good because, as an overview session, it's really hard to go too deep into anything, and so there's always going to be questions. I'm trying to keep this at an overview level. So here we have the Azure Portal is one way that you've seen that you can go and manage your Cosmos DB account. Here you see a snapshot showing a bunch of containers and in various databases. There's also the Azure CLI, where if you click on this link up here, it'll open the CLI. And then here, and you can type out a command here. I'm going to create a database. I'm specifying the name of the resource group and the name of the account and the name of the database and executing the command. And the database has been created. If you're a PowerShell fan, it's a similar functionality with the commandlets available for you to do the same thing in PowerShell. And here I'm doing the very same thing. I'm creating a database using PowerShell. Notebooks are very compelling and relatively new. They've been around for over a year by now, but they're still relatively new and they're getting better. They're Jupyter notebooks, which technically means they're limited to Python, but in fact, C# is supported as well. The SDK for Python and the SDK for C# is embedded in the notebook. The notebook lives on with your Cosmos DB account outside of any databases. So if you delete your databases, the notebooks are still there. And here I'm using the Python SDK to again create a database called my database. And you just hit the run. You just hit the run link and it right here, and it executes. And of course, it all boils down to REST. There's a full API that does everything, but you'll hopefully never have to deal directly with the REST API. Everything gets indexed as you insert it by default. You can improve performance by creating indexing policies that exclude properties. But for the most part, it's not quite the same double-edged sword that you have in the relational world, where if you don't index anything, then your queries will be terrible. And if you index everything, well, then, you know, you're needlessly consuming storage and compute on every insert, update, and delete by maintaining indexes that you don't need. But it's a very different ballgame here. I'll show you why. There's this pattern that they have called automatic indexing, or I would say maybe an algorithm, where if you take a hierarchical document like such that has nested objects and nested arrays, but ultimately there are nodes at the end that are the scalar data points, it takes this hierarchical structure and flattens that into a set of key value pairs like such, and then indexes those such that when you run a query like this, it examines the index and is able to immediately locate the documents. Change feed. I would hope that after I deliver my data modeling session in April, that after that I can come back again and talk to you about microservices. It's a pretty advanced topic, and it's all based around the change feed. So every container, when you insert or update documents into that container, that gets emitted through the change feed, which is a consistent, continuous and persistent log of changes in the order that they occur to the container. And that enables you to do things like replication, where you can replicate a container from one container to another. Denormalize data as is needed very often when you're doing data modeling, which we'll talk about in the next session. Any event of interest that occurs when a document gets inserted or updated, you can examine that document, and if it's an interesting event, you can generate a notification. You can use it to maintain materialized views. So you might have use it to update some other container to reflect the changes of this container, and where that other container is very efficiently queried compared to the source container. Or just simply to move data downstream. As data comes into Cosmos, I need to move it somewhere else. So I mean to maybe archive it to blob storage, and I need to push it into SQL database, whatever it is. You know, all of these are reasons for using the change feed, and you can build microservices for all of these use cases that consume changes from the change feed as a single event source, and thereby providing a dramatically simpler microservices architecture than you would have otherwise if these microservices were codependent on one another and you had interdependencies among the microservices. This is a much simpler and cleaner approach. Multiple APIs and data models. We started talking about this. We went with the SQL API. You saw how that gives us JSON documents. You saw how we use SQL queries to get those JSON documents. But then in that dropdown, we had other choices that I said I'd get back to. So let's also understand that there's the Mongodb API. The SQL API is the core API. If you're starting with a green field and you don't have any compelling reason, and I'll discuss what some of them could be, for going with any other API, you will always go with the SQL API. For instance, it's the only API that supports stored procedures that I was describing. The Mongodb API is there for you if you already have an invested interest in MongoDB, or you are porting an existing MongoDB application, because it's wire level support. So you basically don't modify the front end, you know, or your middle tier at all. You just hopefully merely change a connection string that used to point to a real MongoDB instance and is now pointing to the Cosmos DB account that is using the MongoDB API. But it's still JSON documents. They call them BSON, but they're still, you know, from a data modeling perspective, it's the same concept of JSON documents with embedded, potentially embedded objects and arrays. There's also the table API. Again, you would never go for this for the green field. This is like Azure Table Storage emulation. If you're familiar with Azure Table Storage, you know that it's NoSQL and that it's schema free, but it's like there's flat rows, unlike a JSON document, which can be hierarchical. But otherwise, it's pretty similar. But it's a very, very primitive API because it emulates Azure Table Storage, and again, it's there. It appeals to folks that are already have data in Azure Table Storage and they want to switch to Cosmos DB as a backend without modifying the front end. This is the only this is the only API that I would say you would have a reason to go with for a green field if over the SQL API if you want graph. And if you know what that means, it means that you have a tremendous number of relationships in your data model, where the relationships are more prominent and more significant than the entities themselves that are being related to. And for that, there's the Gremlin API, which is an Apache creation. But internally, you'll see that it's nothing more than just JSON documents that represent those vertices and edges. A vertex is an entity, and an edge is a relationship between any two vertices, any two entities. But you'll see in a moment that those are just surfaced as JSON documents. Then there's the Cassandra API, which, like the Mongodb API, it's the same thing. You know, if you're coming from Cassandra and you have an existing investment in Cassandra and you're porting a Cassandra app over or what have you, but you want to basically treat Cosmo Cv as though it were Cassandra, you go with the Cassandra API. Oddly enough, you'd actually define a schema. You know, there's actually a create table statement where you define the columns because it's columnar, and that's the way Cassandra works. But the reality is that under the covers, so again, these two are the same from a data modeling perspective. It's JSON versus BSON. But of course, with the SQL API, it's the native API, the core API with SQL queries, and with MongoDB, it's however you do things in MongoDB. Under the covers, it makes no difference. You're going to get the same global distribution, horizontal partitioning, automatic indexing, and provision throughput capabilities that you get. You know, you're going to get all that regardless of the API. Because they're under the covers, there's a storage model, a storage persistence layer that's based on keys and values, key value pairs. So it doesn't matter which of these APIs you choose. I'm not going to get into a discussion about interoperability. Generally speaking, they're not interoperable, with a minor exception that you can choose the Gremlin API for graph and still use the SQL API to access that graph. But basically, we're going to stay focused on the SQL API and the core API from this point forward. Throughput and cost. We measure performance in terms of latency or throughput. My favorite analogy is the restaurant analogy. So there's perceived performance, which is when I sit down and from the time I give my order to the waiter until the time the food arrives ready for me to eat. That's my perceived performance, right? But that's going to be latency and throughput. The further away that waiter is from the kitchen, the longer it's going to take that waiter to walk to the kitchen with my order and walk back from the kitchen with my food. And completely independent of that, there's the kitchen that's trying to crank out as many orders as it can that are coming in to, how many burgers can this kitchen produce before you need to hire more chefs and more kitchen equipment. So those are two very different things, right? Latency and throughput. How fast is the response for my request, and how many requests can be served within a specific time. So we're talking now about the latter. We're talking about throughput and request units, which is an RU is like a way that you measure the memory, CPU, and I/O cost of any request. Okay. And it all gets blended together and rolled up into this unit of currency called a request unit. Because requests every request is different. When you issue a request, the response comes back at you. In the header, you will see the cost of that request, the RU charge. So writes always cost more than reads because multiple replicas are getting written to, and whereas when you read, a single replica can satisfy the read. Queries cost more than point reads, and then some queries will cost more or less depending on whether indexes are available or not available, yada, yada, yada. What's nice, though, is that request units are deterministic. So the same request is always going to cost the same number of request units, assuming that the data hasn't changed, which obviously doesn't happen. The data does change. But when you run a query, then the number of RUs that it costs to run that query is going to be the same every time you run that query, assuming that the data hasn't changed, right, in between each time you run it. So you actually get predictable throughput. And you can monitor RU consumption here. If you look at those two, if you look at some of the similar looking queries that we had before, the one on the left. Sorry, it's not. There we go. This one on the left here. where it's a very simple query. It costs just under 3 RUs, which is, by the way, about the cheapest operation, or I should say the cheapest query. A query is never going to cost less than 2.8 some odd RUs. Okay. This is a slightly more complex query, which is cross-partition, and it has array length and starts with it. It'll cost a bit more. It might cost a lot more than this if there was a lot more data, since this is a cross-partition query. There are metrics where you can see the requests. You can see the 429s, which is what you get if you exceed your throughput. If you provision 400 RUs per second for your container, like we saw earlier, that means that within every second, you're guaranteed you will be able to consume 400 request units from 1 second to the next. If you try to push more than 400 RUs within 1 second, your request will get throttled with a 429, and you'll have to do a retry. The SDK will do some retrying for you, but it's not a good situation to be in if it's happening a lot. Here, programmatically, you can see that I'm able to look at the consumed RUs that comes back from the result when I call create item on a container. And we request 9.9 request units to create this document in a container. And here I'm using the C# SDK. See how easy it is? You need to get a client. All you need is that endpoint and the master key. Remember those two things I said earlier that you need? And then you want a reference to the container where you name the database and the container name. Dynamic up a new document. This is beautiful C# feature that blends so nicely with the schema-free nature of Cosmo Cv, where just like you don't need a schema in the database to store a document, you don't need to define a class in C# to define an actual C# object, because this is not a JSON string. This is an actual JSON object supplying that ID, which I told you have to, but I'm using a GUID, and it costs 9.9 RUs. So we just looked at manual throughput, where we provision 400 RUs. That's guaranteed to always be available. You can lower and raise it as needed, so it's really good for predictable workloads, right? So let's say I need 5,000 RUs. I'll provision 5,000 RUs. But it's not likely that I'll always need 5,000 RUs. And if there are predictable periods of time where I'll need substantially less, that will mean there's unused capacity, meaning I'm paying for capacity that I'm not using. So since it's predictable, I can lower it. When I know it's the busy season, it'll be 5,000. When I know it's less busy, and I know when those times are, which is many scenarios, but certainly not all scenarios, then I'll lower it. And this is the most inexpensive way to go about it. And then I'll raise it when it needs to be raised again. With auto scale, it'll go up and down for you automatically, but it's going to cost more. But it's going to cost less than if you have to manage this yourself when it's an unpredictable workload. Meaning you don't know how many RUs per second you need. You just know the most that you'll ever need. Let's say that's 5,000. And then you say, go with auto scale. And it will go up and down between 10% of what you specified, which if it was 5,000, that would be 500. And the throughput will always be somewhere between 500 and 5,000. But it's going to cost 1.5% more. And then there's serverless, which you saw is still in preview, which is consumption-based. So you only pay for the RUs that you use, right? The problem with using autoscale for this is that you're still going to have wasted capacity, because autoscale only goes down to 10%. But what if I'm idle most of the time? Then I'm still always paying for that 10%. And when autoscale does adjust, it only does so on hourly intervals. So for like small demo applications or small POCs that are getting a ping here and a ping there, that still amounts to a lot of unused capacity, and that's why there's serverless. Every request, whatever the RUs are, that's what you pay for. You don't provision throughput, but it's subject to, going cold, and you don't get the same SLAs. I mentioned this already, RUs per second, or how many RUs are available to you. And if you exceed that, you get a 429. You'll see that here in the response header. And here you'll see an exception being thrown for the same reason. There's your 429. And here I'm doing this with the SDK, which means if I'm getting the 429, it means the .NET SDK has gotten multiple 429s behind the scenes. You can see it in Fiddler. There's one, there's another, and here's the third. There's actually, I think, 10 before the SDK will, so the SDK is retrying already. And so if you're getting the 429, it's not a good situation. The 429 is on the portal.
Hey, Lenny, we have a question in the chat of how often can you change the throughput? Could you script something to change every night at midnight or something of that nature?
You certainly could. You certainly could. I would say, though, that depending on how different the throughput setting is going to vary from what it was before to what you're going to change it to, it could be instantaneous or it could take an extended period of time. Meaning, if you go from 400 to 1,000, it'll be instantaneous. If you go from 400 to 20,000, and I'm just guessing here, I think it's sufficiently high, you will have to wait while hardware gets provisioned. But then you'll be able to go back down to 400 instantaneously. And actually, when you reach certain, if you get what I'm saying, but basically, because if you're saying when you only provision 400, not all the hardware that would be necessary to support 20,000 is provisioned. So you might have to take a little bit of an extra hit just that first time. But then you might not be able to drop it all the way down to 400 because they're going to hold on to those resources. You might only be able to drop it down to 800 from that point. But the short answer is yes, you can programmatically change the throughput on a container, and you can certainly, of course, automate that programmatic change on some sort of schedule script basis. I talked about provisioning database throughput earlier and why you don't want to generally do that. It's this check mark up here where if you check it, then you choose your throughput, either manual or auto scale, at the database level and not at the container level. But let's talk about why, so normally you would want to uncheck that and to bring it down to the container level. But let's talk about why you may want to have database provision throughput. So this is what you really want. You want to provision throughput individually on a container. And the reason I have separate containers with different throughput is because I know the container number 5 needs that 50,000 RUs a second, and container number 1 only needs 400. Because I know these things. But if I go ahead and provision 5,000 RUs per second on the database level, that is going to be distributed as 1,000 RUs each, roughly, on each container. And if you're migrating an existing application that might have been inefficiently designed, where there are really a bunch of multiple containers, where really there should just be one, because somebody created them with one container per type, well, then logically you want them thought of as one, and this could be a good way to do it. It's really 5,000 for all of them, because it really should just be one container with 5,000 RUs. Sometimes you need to differentiate solely on the partition key. So you might have 2 containers. Back up here. Right, but different partitioning requirements. All right, so I have 2 containers that logically should be thought of as one from a throughput perspective, but I have to create them as separate containers because they have different partitioning needs, and I have to therefore partition one container one way and one container the other. But in terms of throughput, I want them to share throughput. And you can mix and match these as well, which means I can say I want database provision throughput 30,000 RUs for the entire database. But then I can say this container gets 400 and this container gets 50,000 on their own. And that means that the 30,000 that I provisioned for the database, well, that will be distributed, 10,000, 10,000, 10,000. But that's going to, again, result in underutilization if only one of those 3 containers really is being used. You're paying for 30,000 and you're only getting 10,000. Right? So you got to be careful. Again, this is the best way to go. Provision throughput at the container level. Okay. Oh, yeah. This would be like the dumbest thing to do. Provision database throughput, and then explicitly provision throughput at the container level for every container in the database. Now you've got 30,000 RUs sitting around doing nothing. Okay. I'm going to kind of skip this because I have to pick and choose here. I'm looking at the time. I'm probably going to go till around 15 since I started at about 10 minutes past the hour. So there's this capacity calculator you can go to. You can plug in some inputs and see the estimated cost. But again, I'm not. Let's just talk about pricing, which is what all that's really about.
Yeah. Another question, Lenny. How many containers would you typically need for an application? Is there a rule of thumb or typical?
If you can get it all, into one, God bless. So in our next session, I'm going to show you how to take something like AdventureWorks, which has one table per type, right? And let's bring it down to a database with 9 tables, but it has customers, orders, order details, products, product categories, all those things with 9 tables. You want to bring it over to Cosmos DB. You can create 9 containers. And in our next session, I'm going to whittle that down and show you how to break that down to the fewest number of containers. But sometimes trying to bring it down to one is overkill and going overboard. But the fewer the better. So good. So on pricing, you pay for storage and throughput separately, but typically you'll find that the storage is relatively cheap compared to the throughput. It's $0.25 per gig per month per region. So if you have 10 gigabytes, it's $2.50 a month. And then there's provisioned throughput, which you saw manual. It's 0.008 cents an hour. So you're paying that amount per hour to get 100 RUs per second per region. But there's a minimum of 400 RUs per second. So that's how it comes to that roughly $24 a month, right? So 0.008 cents for 100 RUs with a minimum of 400 RUs. That's how much it is per hour, per day, and therefore per month. That's your kind of minimum. If you go with manual provision throughput, auto scale, gives you that magic, but it gives you that magic for unpredictable workloads, but you pay for it. And they on their documentation, they describe some scenario in which you can actually wind up saving with auto scale, but I think that's just marketing spiel. Honestly, it's just, as you can see, instead of 0.008, it's 0.012. Of course, your RUs are fluctuating between the amount that you specify and 10% of that amount. So it's not going to be $35 a month. It's only going to be $35 a month if you're at the max the whole month. So there could be, maybe it could come out less than $24 a month with auto scale. Depends on your scenario. You'll have to experiment. And then there's serverless, which is great. Believe it or not, it's only $0.25 per million RUs. I couldn't believe that when I first heard that. So, serverless can get you a long way. You don't get those SLAs though. So if no one uses the database for a while, it can get cold, and then your first hit, you'll have to get that little extra delay, kind of like the way an Azure function goes cold. But for 5 million, if you hit 5 million RUs in 1 month, it's $1.25. So very cheap, and there are more options. Reserve capacity. I didn't talk about the analytics storage. There's only so much you can fit into an overview, but there's a very compelling Azure Analytics link and an analytics storage story here, where a column store of your transactional data is maintained in near real time at all times, and then you can hit that analytics store without any impact on your transactional workload, and link that up to Azure Synapse, which is fantastic. But I don't have time to talk about all this. We have to kind of start wrapping things up by talking about partitioning, and maybe a few minutes on global distribution if there's time. We've seen that we get elastic scale by adding multiple servers behind the scenes. So we think of a container as a single logical resource, but behind that single container, there are multiple partitions. And you can think of each partition almost like a computer, each one with its own CPU processing power and with its own fixed storage. So those are what I would call physical partitions. With automatic scale out, where as needed, Cosmos DB will just add another physical partition to manage your growth. So let's see how that works. We work with a container as a single logical entity, but behind the scenes there's this cluster. And as more processing power or storage or both is needed, Cosmos DB will add more and more and more. And there's really no upper limit to how many physical partitions you can have. And each one, like I said, has its own processing power for throughput and its own storage capacity. So there's at least theoretically no upper limit, and therefore unlimited storage and unlimited throughput. Theoretically, you have to partition things properly to achieve that unlimited scale. Well, those are physical partitions. What are logical partitions? I've been using that word a lot. Remember, we define the logical partitions. Let's drill down. We've got 3 physical partitions here. Cosmo Cv is managing these physical partitions. When we write to the container, documents land on any one of these physical partitions. We don't know which, and we don't care which. What we control is, and what we care about, are the logical partitions that are defined by our partition key, which we supply when we create a new container. So if you went with a social networking scenario where I had the username as I've chosen the username as my partition key, that would mean, and if, let's say now forget about the physical partitions, it would mean that all the documents belonging to any one user would be in the same logical partition. And you got to also know that a logical partition will never span physical partitions. All the documents that have the same partition key value will always be in the same logical partition on the same physical partition. And if you supply the partition key with your query, Cosmos DB will know which physical partition to use. And again, because we're schema free, all these documents can be of different types. So you can imagine one document that is the profile document for Tim, then several that would be Tim's posts, more that would be Tim's likes, maybe some are Tim's comments, and likes, comments, and posts, and the profile, they're all structured differently, they're all different types, but they share the same partition key. And so they can be stored in the same logical partition and certainly within the same container. We'll talk more about this in the next session, but in terms of your decision as to whether embed data in a document or to keep it in a separate document in reference, you should know that there's an upper limit of 2 megabytes on a document and 20 gigabytes on a logical partition. Partition splits are one of the beautiful things about Cosmos DB. So here I've got a bunch of documents stored. They're in 4 different logical partitions because there are 4 distinct partition keys. Cosmos DB has put 2 logical partitions on one physical partition and 2 on another. And as I write more documents and create new logical partitions, they fill up. And then at some point, let's say that second partition becomes either too busy in terms of throughput for what I'm provisioned and I'm paying for, or is overflowing on storage. It'll have to split that partition. And Cosmos DB will only split one partition at a time. It'll never like reshuffle the entire cluster. It'll pick a partition and say, I'm going to split you and spin up a new physical partition and move roughly half of the logical partitions over. And then life goes on, and so on and so on. That happens without any interruption in the SLA. You want to avoid hot partitions. This does not look like a pretty picture. So if means I pick the partition key here that is not very well distributed. And from a storage perspective, we've got a hot partition where most of our documents live on this one physical partition and the other physical partitions are underutilized. That's a hot partition. This looks like much nicer distribution. But again, a hot partition is not necessarily a hot partition because of storage reasons. It could also be because of throughput reasons, which is why a creation date is almost never a good choice for a partition key. So from a storage perspective, I'm getting nice uniform distribution of all my data because everything's grouped by the day. But from a throughput perspective, all the writes of the day at least, and perhaps most of the queries, are being routed to one physical partition all the time, and the other physical partitions are doing nothing. So that's wasted. When you provision throughput on a container, that throughput gets distributed across all the physical partitions, whether those physical partitions utilize that throughput or not. And now, basically, if I provision 30,000 in this case for the container, in this case there's 3 physical partitions. That's 10,000 each. I'm paying 30,000. I'm paying for 30,000. I'm only really getting 10,000 because of this poor choice of a partition key. That's a hot partition from a throughput perspective. Cross-partition queries stem from all this. I was explaining this all earlier, so this should be somewhat fresh. But if you supply if the partition key is known, then it's a single partition query. Cosmos DB knows which logical partition and therefore knows which physical partition it has to go to, and it doesn't have to bother with the others. And I could now, again, further filter on Mark to get just his comments or just his likes or just his posts within a given date range. Whatever it is, the fact that the username is known, it's a single partition query. But if you do something like this where user's favorite color is red, well then, hey man, obviously that query has to fan out across all the logical partitions, which means it has to fan out across all the physical partitions, which happens for you automatically, and it's really beautiful and elegant. Like you get one result that's aggregated from all the partitions, and then SDK will even parallelize that execution across the partitions to speed it up. But it's still obviously undesirable if that is your most common use case. Your most common use cases should be single partition queries, and the edge cases should be those cross partition queries. So that's what's going to give you that massive scale. These are just drilling home kind of the same points I've been making. Uniform distribution, not just of storage, but also throughput. I mentioned that you want to minimize those cross partition queries. I mentioned that for stored procedures, the partition key is going to determine which documents are eligible to participate in a transaction that will roll back or commit. You can actually choose the ID property as the partition key, which is kind of an odd pattern you might think, because every document is unique within a container, like I was saying earlier, based on a composite, a combination of the whatever property you choose as the partition key plus the ID. But if you choose the ID itself as the partition key, which you can do, it gives you exactly one document per logical partition. And you might say, well, that doesn't sound like it makes sense, but actually it does for single point, for point reads and writes, where your most common use case is reading and writing a document at a time by a known ID. Well, now you only need to know the ID, because not the ID and a partition key. And you can read and write documents extremely efficiently at a cost of 1 RU. Okay. And so it's also very good for IoT scenarios. But obviously, if you need to group documents together, like we saw before, this would not be a good choice, because it would be impossible to have more than one document in a logical partition. If you have like a small lookup list, you're going to want to put all of them, all the documents that make up that list inside of one logical partition. Remember, a logical partition can handle 20 gigabytes, so you're not going to worry about your lookup lists ever going anywhere near that. If you have a list of states and provinces, what application doesn't have a list of states and provinces? Or if it's an e-commerce site, you have a list of product categories. So what you'll do is you'll create a type property, and you'll set the value of that type property to be the same value for every document in the lookup list. So all of my flight documents, these are all the flights that my airline operates. So it's not my flight telemetry, which is gargantuan. It's just a small list, relatively small. And every document in every flight document has a type property whose value is set to flight. Every airport has a type property whose value is set to airport. And then beyond that, you're going to, again, want to optimize it for your queries. So if you're most commonly using customer ID to read and write orders, then that would be a good partition key. And like I said, for the social networking example, these are documents of different types. One customer with multiple orders in the same logical partition, because they're using the customer ID as the partition key. You can't change the partition key. They're immutable. You can't change them on the document. You have to delete and re-add the document. You can't update a document and modify its partition key. These are certain strategies for what you can do to cope with the pain that you will experience if you need to change the partition key. One common thing that people do is they'll always choose a partition key called PK. Whatever the value is, the name of the property doesn't change, and it's a copy of, let's say, the zip code or whatever it is. And then if you do that and you also use GUIDs or just something that else is globally unique across partition keys, then you will not have any collisions if you have to migrate. When you migrate, you just have to modify the value of the PK property, and you'll never have a collision. But again, the only way to modify the value of the PK property is to do the delete and then an insert. So it's still painful, but this can mitigate that pain. I'm at the end of the presentation. I think I've been going for about an hour. I do want to spend the last 5 minutes covering global distribution because it is super important and super easy. Replication is we replicate for the obvious reasons of performance. within a region. So even if you don't globally distribute, Cosmo Cv maintains replicas of your data. So those black boxes that I was calling physical partitions, that I was saying you can think of it like a regular computer because it has fixed storage and a CPU. It's more than just a box. It is actually a unit of replication. Every physical partition within a data center, within an Azure data center, is replicated 4 times. There are 4 replicas, even within that one region. And that provides with performance and availability, high availability. But if you replicate across regions, well, now you're bringing data closer to the customer. And now we're talking about improving latency to get back to the performance example of talking about being in a restaurant, you know, where the waiter, it takes longer for the waiter to walk back and forth the further away I am seated from the kitchen, right? So this addresses that. Gives you business continuity. That's other obvious reasons. If there's some sort of major disaster in a data center, you've got another data center. And here's a lot of Azure regions globally that you can distribute your Cosmo Cv database to. You can just associate multiple regions with one account, like so. Geofencing policies just mean that some countries don't allow you to, I don't know, some countries you just have to pick multiple data regions within that country. They don't want data inside or out of the country. Don't ask, I don't remember which countries, but there might be some of the usual suspects. It's really super simple to dynamically add and remove these regions. You just click with the mouse the mouse in the portal. And with multi-master, writes as well as reads are enabled in every region. But then, of course, it opens the door to conflicts, and opens the discussion to consistency, eventual consistency versus strong consistency, and those guarantees and the trade-offs, which we're not going to get into. But those things become much more of a concern when you're doing multi-master. I'm sorry, when you're doing global distribution, because within one data center, even though there are multiple replicas, so there is a concern about consistency. When you read from a replica, how do you know it's up to date? Those replicas update often within 1 millisecond of one another. Like, it's extremely rare to get a dirty read, even with eventual consistency in one data center. But once you're spanning multiple regions, you know, obviously, data update, it could take hundreds of milliseconds, which is an eternity relatively. So all those concerns come into play. You just enable multi-master, and you can write in multiple regions, and then there's conflict resolution that can be dealt with in a number of ways. So I'm going to end up with our last demo for global applications, global distribution rather. Oh, I don't have that slide in here? Oh, geez, I'm sorry. Let me see if I can find that for you real quick to end off. That's worth. Sorry, I didn't do a double check for, give me 30 seconds and I will find a deck that has that in it. All right, hopefully this one's got it. Here we go. Perfect. Sorry for that brief interruption, but here's global distribution kind of demo, right? Here I've got a Azure Cosmos DB account in West US. I've also got an application service. It could be an app service. It could be a VM. For demonstration purposes, I've got a VM, but it could be an Azure function. Point is, it's in the same region. And so it reads and writes data to and from the Cosmos DB account very quickly, that the application does. And so if you're a user of the application, you're going to have very good performance, like so, for example. And I ran the same query over and over. The query costs only 2.97 RUs. That's the throughput. The latency, as you can see, under 10 milliseconds in every case. So that's pretty darn good. But if I set up an application server, an app service in Southeast Asia for my Southeast Asian customers, but I don't have a copy of that data in Southeast Asia, and instead the application needs to traverse continents to read and write data, this is the same code running in that Southeast Asia data center. And the cost is still 2.97 RUs because that's the throughput, right? That's the effort it takes to make the hamburger once the waiter gets to the kitchen. But for the waiter to get to the kitchen and back is taking so much longer, right? Although the cost is the same. All you need to do is point and click on that map to stand up a replica of your Cosmos DB account in Southeast Asia. Cosmos DB will, the gray dotted line, the gray arrows are Cosmos DB replicating behind the scenes. So the Southeast Asia customers at this point, will experience the same single-digit millisecond latency, low latency, as well as the same throughput as before. And of course, if that data center should go down, well, then it can always fall back. But normally, you will have the same latency no matter what region your customers are in. And with that, that takes us to the end of the session. I want to thank Dwayne for arranging and inviting me and inviting you all, and thank you for taking the time off of the afternoon to be here. With that, I'll hand it back to you.
Yeah, thank you very much. Appreciate it, Lenny. Thank you very much for that in-depth talk, and looking forward to getting more when you come back in a couple months. So looking forward to taking it a step further. So for those of you that stuck around before you leave, I'm going to post in the chat a link for attending today. Our sponsor, Skylines Academy, will provide you with a coupon code for a free membership, 1-year membership to their to the Skylines Academy training site. So you can get some good training there, some good on-demand training. I know Lenny mentioned he does some training, on-demand training for Pluralsight. So if you have access to that, I recommend you look up his training on Pluralsight. Myself and Brian Gorman, who are on right now, we do training for Opsagility, and a couple things to look for. I welcome you to follow me on LinkedIn or Twitter. We have some free Saturday fundamentals courses coming up in the next couple months, where we're doing like a Saturday AZ 900 course, a Saturday PL 900, a Saturday MS 900. We're offering some free Saturday training to you, and that should go out on social media here probably in the next day or so. So welcome. That's free live training. So you'll have a live instructor doing that training for you. So if you're interested, welcome you to follow me, because once it goes out, I'll definitely be resharing it out there. So hope to maybe see some of you there as well. So otherwise, I want to thank you guys for sticking around and sticking with Lenny as he provided this great overview of Cosmos DB. Real powerful use of a NoSQL database. Very, very cool. Looking forward to having you back for a couple additional sessions around it. So,
I look forward to it as well. Thanks again.
Hey, Lenny, this is Brian.
Hi, Brian.
I had a quick question, if you don't mind. One last question. I'm a traditional relational DB .NET web developer, and I was just wondering, is there a situation when I should be like, hey, I should probably think about doing this in Cosmos DB rather than SQL, and why?
The 3 V's: volume, variety, velocity. From a storage perspective, if your storage needs are busting out of SQL, if your throughput needs are busting out of SQL, and then from a schema perspective, the importance of strongly typed data. If you don't really need the volume and velocity V's, and just the schema-free variety. You have JSON support in SQL Server. But if you are storing everything in JSON, and I can do a whole talk on just JSON in SQL Server, when it's appropriate, when it isn't. But if you find that you're basically using JSON everywhere in your SQL Server database because you want to enjoy not having to do alter table add column or alter table drop column, you want to avoid the disruptive nature of schema changes that often involves, the full stack. It's very disruptive, right? Because then you have the ORM layer over that, right? Entity framework and whatnot, right? And if you want to cut all that out, because you don't have, really any type of schema. Just imagine, the way we saw a document stored in Cosmo Cv, where everything's pre-joined, right? The customer has all of their, has all of their addresses. A customer document has all of its address documents. An order document has all of its order detail documents nested within it. So, there's no need to join when you're selecting. And then once you've selected and the user's made changes to both the parent and the child, and maybe a nested child, can be very complex graph. Then, the overhead of entity framework and figuring out which tables need to be updated and then issuing those updates, updating separate tables. But all that goes away with Cosmos, right? Because the document in the database is essentially a serialized representation of the entity in the application. So that whole ORM layer goes away, and that's is the word entitled. It's attractive, but it's also goes very much against the grain of traditional relational database developers. I consider myself as well. My current project is using SQL. And only SQL, no Cosmos. It's using SQL Server, and everything's strongly typed, and we've got all our constraints and all those things that you don't have in the NoSQL world. If you want to stick to those, then stick to those. Really, it's about global scale, global distribution, right? The things that are built into this platform. If you need that elastic scale, planetary scale, and unlimited growth, you don't have unlimited storage and unlimited throughput with SQL Server. Right, it's a scale-up architecture. Right. Just some ramblings of a crazy old guy here.
No, that's awesome. Thank you so much for taking the time to do that, to answer that.
Yeah.
Great. Anybody else have any other questions? Nope. Silence is compliance, right? All right. All right, Lenny. Thank you very much. Thanks, everybody. Have a great day. And look forward to seeing everybody again soon.